All right. I think everybody in Zoom has already mentioned that they are present. Let me send out a roll sheet for those people who are physically here, and then we'll get cracking on today. So we're going to start today by looking at the common base amplifier with the early effect included, because I was kind of rushing through things last time. So let's take a few minutes to actually figure out what's going on here. Just to be clear, we were able to calculate all of our amplifier parameters for our common base amplifier without the presence of early effects. So just to revisit those things, the input resistance was approximately 1 over the transconductance. The output impedance was simply the collector resistance RC, and we found that our voltage gain for this amplifier is GM times RC. So it's the exact same thing as the common emitter amplifier, except that it has a positive value. Because we have the exact same gain constraint or gain equation for the common base amplifier as the common emitter, it also has that same constraint that the magnitude of the voltage gain is going to be less than or equal to VCC minus VBE over VT for the exact same reasons. If we try to increase it past that, we push things into the saturation region where it's no longer going to behave well as an amplifier. All right, so common base with the early effect. So it's going to look like the exact same amplifier we had above, so I'm not going to bother drawing it again, but we are going to go into our various parameters here in a more detailed way. So let's start with our input impedance. So we're going to have this exact same representation, except between our collector and emitter, there will now be a resistor. So let's just redraw that real quick like. See, here is my input voltage Vx, Ix. Short out my base because it's the small signal model. And between the collector and ground, I have that resistor RC. I believe, as I mentioned at the very tail end of last class, we could redraw that like this. So this node up here is our emitter node, and this node down here is our base node. And between the emitter and the collector, we have our resistance R0, as well as our dependent current source, where the current should be directed from the collector to the emitter, having a value of GM V pi. And then over here between the collector and our base, we have our resistance RC. Doing a source transformation on the dependent current source in parallel with that resistance R0 and combining the resistors R0 and RC into a single series equivalent resistance would give us the following circuit. So here is Vx. Here's my quantity Ix that I'm interested in. Here I have R pi. There's V pi. I'm going to have R0 plus RC here. So that comes from RC being in series with R0 after I do that source transformation. And then here is GM V pi times R0. And if I use Kirchhoff's current law, I can see that my current Ix is simply going to be Vx divided by R pi. So that's the current flowing down through that resistor R pi. And then I'm also going to have to express the current flowing to the right through that combination resistance of R0 plus RC. And so that is going to look like Vx minus GM times V pi, where V pi in this case is what? Negative Vx, right? Opposite polarity. Times R0. This whole thing gets divided by R0 plus RC. So I'm going to now factor out a common term of Vx, and I should get 1 divided by R pi plus 1 plus GM R0 over R0 plus RC. And from this, we can see then that our input resistance is Vx over Ix to the minus 1 time. So just something here. All right. So what's happening to our input resistance with the early effect included? Another person saying here. All right. So recall that we had R in, so without early effect, was simply roughly 1 over GM, right? Well, we could say that, let's see, since GM is, actually, let's do it this way. R pi is beta over GM, then that would imply that 1 over R pi is GM over beta, right? So if we put in effectively GM over beta, right here, we're going to have something similar to 1 over GM, but it's going to be even smaller because we're dividing it by beta. And then we're also going to have this other term that is effectively in parallel with that small resistance, right? When I have 1 over a resistance plus 1 over a resistance, and then I take the reciprocal of that whole thing, that's me taking the equivalent resistance of resistances in parallel, right? So I am arguing that I have a 1 over GM factor that's divided by beta, so that that resistance portion is very small. And then in parallel to that, I'm putting in something else. So best case scenario, I'm going to have a resistance that is very small in comparison to what we had before the early effect was included, right? So including the early effect here then shows that the input resistance of this particular amplifier goes way down, significantly down, almost by a factor of beta. That could be bad news, or it could be good news. The instances where it could be good news is as if we were trying to provide impedance matching. And so what I mean by that, we saw values of R pi on the order of a couple of kiloohms earlier, right? So if we divide R pi by beta, we're getting somewhere on the order of tens to hundreds of ohms. Well, that can be a good thing if our input source has a low source impedance. So if we were trying to connect an antenna or something like that, the impedance of free space, have you guys had Physics 202 yet? Okay, so the relative impedance of free space is around 377 ohms. Most connectors that we use in the lab have an impedance of somewhere around 50 ohms to 75 ohms. So this methodology provides us a good way to match those low impedance sources that we might see on the front end of an RF amplifier or something like that. So just because we've lowered the input impedance here and we're dealing with an amplifier that has particularly low input impedance to begin with, isn't necessarily a bad thing. It's bad from the comparison to an ideal amplifier, but it does actually have applications that are useful. All right, so let's look at what happens to our output resistance, okay? Or output impedance, excuse me. All right, so if we were measuring our output impedance, we would be looking at the following circuit. And I'm going to be doing this trick several times today. It's not really a trick per se, but because I'm looking at the output impedance, I short out my input, and because this is a common base amplifier, I should also be shorting out my base terminal and looking in through this guy, right? Inherently, if I'm trying to figure out what the output resistance of this circuit is, this is what I'm doing. So my question to you guys is, how is this any different from when we looked at the output impedance of a common emitter stage with the early effect included? So let's look. Common emitter stage, scroll way back up here. Common emitter amplifier. So when we're looking for our output impedance for our common emitter amplifier, we notice that the emitter is grounded, and because we're looking at for the output impedance, we would ground the input signal as well, which in that case was the base terminal. So we have the exact same conditions it should stand to reason that the output resistance should be the exact same thing. So we don't need to do any extra work. Cameron, what's up? No, not at all. As long as the arrow is directed away from the base, that tells you that we're dealing with an NPN transistor. But even there, because we're dealing with a small signal model, and the small signal model of the NPN and the PNP are identical, it wouldn't matter if the arrow were directed the other way too. But yeah, it does not matter whether we put the base on the left-hand side of the circuit or the right-hand side of the circuit, as long as we have the resistor between the power supply and the collector, and then we're grounding those two terminals. They are absolutely identical. So with that in mind, I don't know what I did with my notes for the common emitter. Oh, wait, here we go, with early effect. It's literally written right there for me. So that was RC in parallel with R out, or R not. And so I'm just going to copy that down directly. R not in parallel with RC. Don't have to do any work whatsoever for that because I already know how that particular thing behaves. Right? That's the beauty of how we've been approaching this, is we're breaking it up into digestible pieces, and things that we recognize, we can say, oh, we know how to do that. We don't need to keep doing it over and over again. All right, voltage gain. So this is going to be a little bit different than things we've seen before. So let's take a minute to draw our small signal model. My input voltage goes here between the emitter and ground. Between the base and ground, I just apply a short circuit. And between the collector and ground is where my resistor RC resides. And my output voltage is the voltage drop over that resistor RC. Excuse me. So I'm going to redraw this guy to make things a little bit easier, in my opinion, to look at. Just to be clear here, this is my emitter, this is my base, and this is my collector, right? So can we all agree this is an appropriately redrawn version of our small signal model? Start there. All right. So I would argue that if we apply Kirchhoff's current law at our collector node and use Ohm's law, we can actually pretty easily figure out our relationships here. So what I mean by that is we could say that the voltage drop over our resistor RC, V out, is simply going to be RC times the total amount of current that's flowing through it, right? So I made a mistake here in my notes, but that'll be okay. We'll figure it out here. So I'm going to have this current and this current add together and flow through that resistor RC, right? So for the topmost current, that is simply Vn, the voltage at the left-hand node of that resistance R out, minus V out divided by R naught. Easy enough. And then I'm also going to have negative GM multiplied by V pi, representing my bottom current branch, where V pi is exactly equal to negative Vn. So I'm going to break things down a little bit here. I'm going to have V out plus V out times RC over R naught is equal to Vn times RC over R naught plus GM, or VM times GM, excuse me. Everybody okay with that algebra there? Anybody see anything wacky here? All right. So if I factor out V out, I have 1 plus RC over R naught. And on this side, if I factor out Vn, I have GM plus RC over R naught. And so my voltage gain is then V out divided by Vn is GM plus RC over R naught divided by one plus, I've made a mistake somewhere here. So the reason why I'm saying I've made a mistake is because the units don't work out. I'm missing something being multiplied by GM. Okay, so I did not carry through an RC. So this factor RC right here is multiplied by positive GM times Vn. So I need it there, which means I need an RC, GM RC here. Which means I need a GM RC here. And then over here, I have RC over R naught. So I have my original gain, GM RC, divided by a factor of 1 plus RC over R naught, meaning if RC and R naught are comparable, have comparable values, that's not really influencing my gain a whole heck of a lot. But if RC is much greater than naught, then this is lowering my gain significantly. And to that, I'm adding, good God, what is this? A factor of RC over R naught so the early effect, depending on how RC compares to R naught either increases or decreases my gain. So kind of a mixed bag here, okay? All right. So now let's start playing around with the different ways that we can bias this thing and what effects that they might have, right? So when we did the common emitter amplifier, one of the first things we did is we figured out what happened or what the results of degeneration did to our different parameters. And for the common base amplifier, emitter degeneration is actually pretty easy to look at. All right, so our circuit in question is going to look something like this. Here is Vn, and then here is our emitter degeneration resistor Re. Okay. All right. So if we want to determine our amplifier parameters, we are going to get to do some simplifications here. Amplifier parameters. All right. So for instance, if we're looking for our input impedance, that would be like looking at this circuit. Let's see, here's RC. Here is RE. And we're looking in through here, right? Fundamentally, this is what I'm doing. So I'm leaving my output terminals open circuited, looking in through the input terminal and trying to figure out what input resistance I see. Well, our signal sees two paths, right? We have one path directed down where we just see the resistor Re. So between that input point and ground, we have that resistor Re. And in the other path, we see our base, or our common emitter core, right? Anybody not see that? So common emitter core, go back up here, is this guy. So if we were ignoring V out and looking in, this is the exact same thing that we see when we're looking in the up direction from that terminal, right? Well, we know what the input resistance of our common emitter core is. And so we can see pretty easily that Rn is just Re in parallel with 1 over Gm. No further analysis required. So looking at it with emitter degeneration, pretty straightforward for the input impedance. For our output impedance, the circuit we would be looking at would be this guy. Since we're shorting out our small signal input, that means that there is no voltage drop over our resistor RE, so it doesn't do anything. So from the output terminal, even with emitter degeneration in there, it still looks exactly like a common emitter core amplifier. And so we can say that R out is simply RC. Don't need to modify anything there either. Now our voltage gain, we are going to have to draw our small signal model, but we'll see that it's rather easy to analyze. So here is our base, here is our collector. This is our emitter. And then down here is going to be our ground terminal. All right. So between our emitter and ground, we have that resistance RE. I'm going to tuck it in right here. And we also have our input signal, Vn. Between the base and ground, we have our short circuit, and between the collector and ground, we have our resistance RC, over which we take our output voltage. So, Bosniak, you're a smart fella, paying attention it seems like. What's my voltage gain going to be here? So what's the current that's flowing through that resistor? RC. Yeah, current flowing through the resistor RC. Negative GMV. Right, so negative GMV pi, where V pi has what relationship to Vn? Sorry for putting you on Front Street here. Same but opposite polarities, right? Yeah. So our voltage gain, or excuse me, so we have V out is still equal to negative GM V pi times RC, which is negative GM negative Vn RC. And so our voltage gain is simply GM RC. So this emitter degeneration here doesn't change our voltage gain at all. Doesn't change our voltage gain one bit. Doesn't change our output resistance one bit. It does serve to lower our input impedance further. So since it doesn't have any effect whatsoever on the voltage gain, you may be wondering to yourself, why are we bothering to include it? Seems reasonable, right? So let's look at our signal here, okay? If we didn't include it, so let's say, I'm gonna put it in here. If we didn't include it, it would represent an impedance of an open circuit from that point in the circuit to ground, right? Well, if we have our small signal VN. When we bias this guy, that's the issue with it, sorry. When we bias this guy, if we don't have that included, there is no signal path for our collector current to reach ground, right? If we don't have that emitter there, and there is a open circuit between, or excuse me, a capacitor between our input signal and there. So let me draw a quick picture here of what I'm trying to explain. So let's say that I have this guy, Vn, some capacitance, let's call this CS because it's connected to the source. Then I have this guy, here's VB. Here's my resistor RC, and here's VCC. And then I have a big open circuit right here. My bias point for this circuit is IC is 0 because there is no path for my collector current to reach ground. So the whole purpose of emitter degeneration in a common base amplifier is to provide a signal path there, using best practices for decoupling your input from, decoupling the input signal from the bias point. So if we don't do that, we screw up something pretty appreciably and our amplifier doesn't work at all. So our bias point is 0, our transconductance is 0, which means everything is 0. All right, so let's take this one step further and throw in some base resistance. With emitter degeneration and base resistance specifically, all right? So we're moving towards our full bias circuit. So this guy would look something like this. All right, so this is what our circuit would look like if we had both emitter degeneration and a base resistance included. This doesn't look like anything that we've really dealt with to this point. So we're going to be doing the small signal model for a couple of these. So just to make sure here, let's see. Amplifier parameters. And I ran out of room. So I'm saying that I don't believe to this point we've analyzed a circuit that looks like this. We've analyzed a few things that are close, but none of them with our base resistance included, which may have some effects. So we're going to have to small signal model analyze this guy, all right? So our small signal model, try to sneak it in over here. Should look something like this. Here's R pi, B pi, GM V pi. Here and here. This is my ground. So, so between my emitter and ground, I have that resistance RE again. I have my test voltage source Vx, and I'm trying to find this current Ix. Between my collector and ground, I have that resistance RC, and between my base and ground, I have that resistance RB. So is that accurate? Let's start there. All the resistors taken into account, all that kind of jazz. All right. So I'm going to redraw this guy because this looks pretty ugly. So between my emitter and ground, I have my voltage source Vx and that resistance RE. And I also have a different path from my emitter to ground if I go this way, right? Which would look like the resistance R pi in series with the resistance RB from the path from emitter to ground. So here's R pi, here's RB, and this node right here is my base. So should be positive, negative V pi, like so. Then I have from my collector to my emitter, so let's put my collector over here. I have a dependent current source, GM V pi. Here's that resistance RC. And this guy right here is my current of interest, IX. Right? Cameron, what's up? I'm sorry, I couldn't hear you. I'm trying, so going from here to here or from here to here. So I'm just trying to make it look, effectively look like a circuit's one circuit that I know I can easily analyze. That's my goal, is instead of having all these weird things with the input signal that I'm interested in somewhere in the middle, I'm moving it to one side so that I can just do simple KCL, KVL, those types of relationships. Just I'm trying to make it as simple as I can. And since I spend, except for this quarter, most of my time teaching Circuits 1, I want to make it look like a Circuits 1 circuit. That's my goal. So in this particular case, I could apply, now looking at this thing, I can see that I can apply Kirchhoff's current law and figure out what's going on relatively easily, okay? So if I apply Kirchhoff's current law, what I'm gonna do is I'm gonna say that Ix is simply this current plus this current plus this current, right? So that would give me Ix is equal to, so the current flowing down through resistor Re is Vx over Re. The current flowing down through that middle branch is Vx divided by R pi plus RB. And then I'm going to have minus GM times V pi. So I need to figure out how I can express V pi in terms of that voltage Vx. And this is another reason why I redrew it this way. I can easily see that this is a simple voltage divider, right? It's two resistors in series connected to that voltage Vx. So I can use voltage division and say that V pi is negative Vx because I'm getting the voltage with a positive polarity on bottom times the resistor I want the voltage drop over, which is R pi, divided by the total series resistance, which is R pi plus RB. So my input resistance then, Rn, is going to be Vx divided by Ix. So if I factor out Vx from the thing I have above, I have 1 over Re plus one over R pi plus RB plus GM times R pi, which is just beta, divided by R pi plus RB to the -1. And so collecting like terms, this looks like 1 over Re plus beta plus 1 over R pi plus RB, and then to the -1 power. Everybody, excuse me, okay with my algebra there? And recognizing that GM times R pi is by definition beta. A little bit tricky, but nothing too crazy here. All right, let's look at our output resistance or impedance. So for that circuit, I am going to be looking at this guy. So let's see, there's RC. There's my output terminal. Here's my resistor RB. It's grounded. And then I'm grounding my input terminal, right? So if I ground my input terminal, here's RE is in there, but it gets shorted out, so it doesn't really do anything. And I'm looking in through here. I would argue that this looks identical to a common emitter stage with emitter degeneration, because I'm grounding my, so here, I guess it's a little hinky here. If this guy weren't grounded, it would be obviously the same as a common emitter stage with emitter degeneration. But if we look back at our notes here. So let's look. Common emitter with degeneration. The degenerative resistor, RE, actually doesn't do anything to change our output resistance, right? So with it there or with it not there, the answer is still the output resistance is simply RC. So I'm going to say R out is equal to RC and call it a day. You don't need to do anything else. All right, lastly here, we're going to look at our voltage gain, burning through the pages. And so we're going to have to use our small signal model for this guy. So here's R pi, V pi, GM V pi, between the emitter and ground, I have my input voltage in parallel with my degeneration resistor. Over here, I have my resistor RB. Over here, I have my resistor RC. Here's where I'm taking VF. So not going to put Posniak on Front Street again this time. I'm going to do it to somebody else. Just kidding. Here's my collector triple. All right. So by this point, it should be old hat to recognize that V out is simply negative GM V pi RC for pretty much every configuration we've seen for these guys, right? So how can we figure out what V pi is in this case? Voltage division, right? We have the exact same conditions that we had earlier. So V pi is negative Vn R pi over R pi plus RB, right? So if we substitute that in up here, we will get negative GM, negative Vn, R pi over R pi plus RB. This whole thing times RC. And from this, our voltage gain is simply V out over Vn is beta RC, because I have a GM multiplied by an R pi, so that's where that beta is coming from. Then I have down here R pi plus RB. So we can see that having this base resistance RB is inherently going to lower our voltage gain, right? So if we left things in terms of GM, which we could have easily done here, we would have had GM times R pi times RC. So we would have been multiplying by a factor of R pi, and then we're dividing by a factor of R pi plus something else. So inherently, this base resistance is lowering the voltage gain of our amplifier circuit, which is bad news. So we're going to talk about how we can effectively bypass that effect in a little bit, just like what we did when we bypassed the emitter degeneration resistor for our common emitter to get rid of that negative impact on the voltage gain. But before we do that, we now need to look at common base amplifiers when there is a source resistance included. And this is going to be really similar looking to what we have with emitter degeneration, but it's slightly different, okay? And so we need to pay attention to that nuance.
Dr. Hartman, can you show please the output impedance formula for the last problem?
It's RC.
Okay, thank you very much.
Yep. All right, so common base with source resistance. All right, so what that's going to look like, something like this. Oops, sorry, VN. So it looks extremely similar to an emitter degeneration scheme, except that we're applying the voltage at the other terminal of that degenerative resistor, which it's slightly different and it's going to be impactful in a couple of different ways. But this is our circuit that we're going to analyze. So for our amplifier parameters, as usual, we'll calculate our input impedance first. And so this is going to look like we are analyzing this circuit when we turn off everything that needs to be turned off. So we can ignore the output terminal, short this guy, and here is RS, and we're looking in through here. So what does this look like? I drew a line using a more obvious color. I simply have a resistance RS in series with a common emitter core amplifier, right? So my input resistance is simply RS plus 1 over GM, because the input resistance of my common emitter core, which is in series with this guy, is simply 1 over GM. So that guy, pretty simple. Let's look at our output impedance. All right, that look familiar? Looking in through this terminal, or excuse me, should be R out, excuse me. Is this topology familiar? It's the exact same thing as a common emitter with emitter degeneration, which we just found out 3 minutes ago was RC. So we're good there. For our voltage gain, what we are looking at is this guy. RS, round that, V out, RC. So if I draw my line here and break this guy into two stages, I'm going to call the voltage at this node here VE. It's connected to the emitter terminal. So it's the emitter voltage with respect to ground. All right? I know what the relationship between V out and VE is very easily because it's simply representing a common emitter core amplifier. So I can say that my voltage gain is going to be V out over VE multiplied by VE over VN, just breaking it up into two stages exactly like we did for our common, more complex common emitter amplifiers. Well, I know that V out over VE is GM times RC, right? Spend that. So that's that you need the voltage gain for the common emitter core. And now I need a relationship that's telling me what VE over VN is. Any thoughts? So what does my input signal see? It sees just what we said it saw when we calculated our input impedance, right? So we have effectively this guy. Here's our nodal voltage VE, and between node E and ground, it sees the input resistance of the common emitter core, which was 1 over GM, right? So using voltage division, we're going to have GM to the negative 1 over RS plus GM to the negative 1, which is going to give me RC over RS plus 1 over GM. Let me be explicit here. VE is VN. Shit. So analyzing this guy with the base, or excuse me, with the source resistance, pretty straightforward. We already had all the building blocks that we need. The last thing that we need to do then before we get into the full-on circuit here is figure out what happens when we have a source resistance and a base resistance. And for the most part, it's going to be fairly straightforward, other than the voltage gain equation. All right, so common base. You know what? We'll visit this on today's Friday, right? Monday, because there's a couple of things I want to talk about with regards to your exam and your homework problems that will probably take up the full 10 minutes. So let me pull up my emails real quick. I'm going to be posting this online. Oh, wait, actually, it's in my Dropbox. So I'll close that. I don't need that. Let's see. Dropbox. ELEN 335. Exam 2 study guide. I'm going to post this online, but I just want to talk about something very important. Open the file. There we go. All right, it says exam 1 study guide. It should be the exam 2 study guide. I'm going to blame Prashant on that. Test format and content is going to be the same. It's a combination of multiple choice problems and numerical solution problems. There is a big list of all of the topics that will be on the exam. It is effectively chapters 4 and chapter 5, the whole dang thing. So we've gone through all of that. Really, the only thing that I think I need to talk about that I maybe haven't is some very, very basic, like gain limits and amplifier trade-offs here. We haven't talked about too much. And there is one terminology concept that I've skipped past that I'll need to go back and revisit, and we'll do that on Monday. Sum total, this is 7 minutes of material, so it's not going to be that big of a deal. All right. The big deal here is the test environment, and starting about down here, the test will be open notes, okay? Because we didn't want to make an 18-page equation sheet, the test is going to be open notes. That being said, it has to be handwritten notes. So we will not allow you to bring, sorry, Ronnie, your tablet to take the test, nor will we allow you to print off the notes from your tablet, because then you could just hand them to somebody else, and that way the entire rest of the class doesn't get to study because you did a good job of it. So I'm telling you this now so that you have the entire weekend and then up until Wednesday night to hand write out and organize your notes. So you can bring as many pages as you want. There is no limit. I don't care if you bring out worked out example problems and worked out homework problems and all that kind of crap to give yourself refreshers. No problem from me whatsoever. It just needs to be handwritten documentation, not a computer printout or anything like that. So we all clear on that. Okay. So that is a fairly big revelation. So like it says, you can't bring printed out notes, you can't bring the textbook, you can't bring PowerPoint slides, which I haven't made any, so that's, you know, I don't know if Dr. Batari has or not. You will also not be allowed to use any electronic devices other than an FE-approved calculator during the exam, which is standard boilerplate stuff. All right, so any questions with regards to the examination? I believe it even says up here, the test environment, IESB 318 at 6 p.m. on Wednesday, 2/3/2021. So we have the date, we have the time, we have the restrictions on what you can and cannot bring to the exam. We good? All right. So the other thing that I wanted to talk about is homework 7, problem 3 on web work, because there is an error here. So this problem is a common base amplifier, although you're only asked to calculate the DC operating point. So it really doesn't matter what kind of amplifier it is at all, because you're only doing the large signal analysis. That being said, you need to treat this problem as if there were a capacitor placed between the input voltage signal and the emitter of transistor Q1, meaning this circuit is simply a 4 resistor biasing network, or a voltage divider with emitter degeneration, or whatever you want to call it. Because whoever made the problem neglected the fact that when you're doing the large signal analysis, you should be shorting out VN, which would short out this resistor R3. They did not take that into account, but it should be. So I'm telling you, imagine there is a transistor placed between VN and the emitter, and everything works okay. Sorry, capacitor, yes, that's what I meant, capacitor. Okay. So, yeah, person who made this problem, like Dr. Batari and I discussed it yesterday, and I am correct that the way that it's drawn, this BN shorts out this R3, which would make this a simple resistive divider biasing network without degeneration, but the answer that WebWork has includes this degeneration resistor. And I don't trust myself to edit the WebWork source code enough to not break everything. So I'm just telling you this for now. Okay, so that's what that is. Let's see what's going on in the chat here. So for the students who wrote their notes entirely on their computer, like I said earlier, you have 5 days to rewrite them all by hand on paper. So do that. If you bring in a computer printout, I will take it from you and I will throw it in the trash. Have I made myself very, very clear? There was also another question, am I going to post all of the Zoom recordings before the exam? Yes, I'm going to try to get all of them up this weekend. Hopefully all of them by, I was going to say tomorrow, but I got to go grocery shopping for my mom and crap like that. So definitely on Sunday, they will all be up. All right, so we clear. People on Zoom and people physically present. We all on the same page as to what is expected for the exam and for this particular homework problem. Will we have 75 minutes for the exam or 90? Right now it says 75 minutes. I'm going to work out the test this weekend because we have already gotten it made out so that we're just checking for typos and things of that nature. My best guess is we're going to allow the 90 minutes just like we did last time. But we're officially saying 75 minutes so that we don't get yelled at. But I believe that we will give you 90 minutes. If Dr. Batari pushes back on that, I will tell you on Monday. Yes, Cameron. So do some textbook problems. The reason I say that is because we didn't really do a whole lot of problems with numbers in them as examples. But for the most part, I mean, all of the problems that you're going to be asked will effectively be broken down into 2 different things. It's either going to be a DC operating point question, which means doesn't matter what kind of amplifier it is because the amplifier parameters don't, you know, they come from the DC operating point, or it's going to be an amplifier that you need to identify, right? So if you can get good at calculating the DC operating points of the different things, so self-biased versus the 4 resistor setup versus the resistive divider biasing, which I believe I developed equations that literally you could write down and be able to put the, I believe we set all of those up as 1 equation, 1 unknown systems that you can calculate either VBE or IC for to get that pretty quickly. That's going to take a lot of the stress off of you doing the other stuff, right? The only thing that you have to remember past that point is the fundamental relationships for transconductance. So IC divided by VT gives you the transconductance. Let's see, R pi is beta over GM. R naught is, how did I remember that one? It's in your notes, that's what it is. I can't remember it off the top of my head because we haven't worked a problem that used it in a while, so. Yeah, so working some problems from literally any electronics textbook would be probably your best bet here. I will say, and I know that I always say this, but the exam honestly seems pretty trivial, especially for a completely open notes test. I'm not telling you that to say don't study. But to me, everything is pretty dang obvious as to what we're expecting you to do. And we've built enough framework to where if you go back through your notes, you could say, oh, this circuit looks like this one, so this is what I'm supposed to do. Even if we didn't do numbers, you should be able to look at it and say, it's one of these, or it's one of those. That's the whole point of how we've been approaching this.
That's what I think.
So let's take a quick look and say what this does or doesn't look like. So small signal level, and this is what we're going to be getting to momentarily, what's the purpose of this capacitor? What does it do for the small signal model? It's a short circuit. So it's a short circuit from the base to ground. So what does that mean for resistor R2? Up here in the small signal model, it's grounded. Down here, it's grounded. R2 gets thrown away. For R4, ground and ground, it gets thrown away. So this capacitor is eliminating that base resistance, which is lowering the overall gain of the amplifier. That is how you do it. You just put the capacitor here for a common base amplifier, where for a common emitter amplifier, you put it in parallel with this guy. That's it. All right. So
I guess that's the trick, is to redraw it.
redraw it as a simplified version and then see what the hell it looks like. Yeah. So for the small signal model, replace all your capacitors with short circuits and then, yeah, redraw it, and it'll look like something familiar real fast. All right, that's enough out of me, and I have a meeting to go to in 10 minutes. So see you guys on Monday.